So Markovnikov's rule, if this is the mechanism, if the mechanism involves making a cation, you're going to get the more stable cation. All right, we're going to see in chapter 8 some chemistry where you don't get the Markovnikov product. We would actually call this. This would be the Markovnikov product. Markovnikov. And then, the other one. This would be the anti-Markovnikovs. Anti-Markovnikov product. In addition to an alkene, there's only two options. H goes on one carbon, X goes on the other carbon. Right? So you got Markovnikov's product, follows Markovnikov's rule, you go through the more stable cation. The anti-Markovnikov product, if you were to see the anti-Markovnikov product, what that says is the mechanism isn't what I've just shown. Right? If the mechanism involves a carbocation, it will be the more stable carbocation. So if you see a product that comes from the less stable carbocation, what that tells you is your mechanism's wrong. It didn't go through that less stable carbocation. And we'll see an example of that down the road. All right, let's do another one. And this one again, this one's going to mimic, this one will mimic take a look at that and think about what the product might be.
Is that H3O and H2O on the bottom?
Yep. All right, now that you've thought about it for a minute, this set of reagents will add HX where X is OH. The H3O plus acts as a catalyst. So now just figure out what the product is, and then I'll go through the mechanism.
I might be getting ahead of myself here, but is there like A1 and A2, just like there's E2 and or E1 and E2?
Yeah, no. They're not in the spirit of your question, the answer is yes. Right? So there are addition reactions that are one step. All the reactions in chapter 8 are going to be multi-step reactions. So yeah, I think you see, the first time you see a single step concerted addition reaction is in Orgo 2. I think we have any in Orgo 1. Okay, so the product, again, Markovnikov's rule, the H is going to go on the less substituted carbon, the X on the more substituted carbon. So in that case, this would be one didn't show up on the board at all. Ooh, sorry. So that's going to be our product. I'll draw the H in, right? There's obviously 3 H's up on that carbon, but that, you know, one of those H's comes from the reagent. Okay, so H3O plus in water is going to add water. This is an acid catalyzed hydration. Okay, so in chapter 7, you guys saw the acid catalyzed dehydration of alcohols to give alkenes. And again, it's just going to be a reverse process. It adds a couple of steps. The other thing I would want to point out, this could be, you could do this reaction with an alcohol instead of, right? We could use an alcohol instead of water here, in which case, instead of adding OH, we would add OR, and you'd get an ether. All right, I've talked a lot. Let me draw the mechanism, so I'll let you, a couple people still writing. The other thing you're going to see here is why we have to have water. Or sorry, why we have to have acid. All right, so if this was simply HX and the alkene attacking the cation, or sorry, the alkene attacking water, right? So if we did that, you'd get hydroxide. And again, so the carbocation is a really strong Lewis acid. The hydroxide is a really strong Lewis base. Right? You're never going to see reactions like this where we go from a weak, water's a weak acid. The alkene is obviously a weak base. You're never going to have a reaction where a weak acid and a weak base give you a strong acid and a strong base. Somewhere in the reagents has to be a strong acid or a base. And so we need, so none of this is going to happen this way. What we need just start over. So what we need here is a stronger acid, like H3O plus. Okay, so now this reaction, we've got a strong acid, weak base, but a strong acid. We're going to generate a strong acid and a weak base. Right? So now this reaction, again, if this was the whole reaction, probably the products wouldn't be favored, right? The alkene and H3O plus are at least as stable as a carbocation and water. But it's not the end product. So now the next step, remember, this actually makes our, I'm probably overthinking the colors, sorry. This makes our CH bond. We have to make a CH bond going from the reactants to the product. The first step makes our CH bond. H goes on the less substituted carbon, gives the more substituted carbocation. And now water will attack that carbocation. Water attacks, not hydroxide. So now we've added an H, we've made the CH bond, we've made our CO bond. And now another equivalent of water has to come in to get to the final product. Another equivalent of water has to come in here, take the H from the protonated alcohol. That makes our product, right? So if we take one of these H's from the protonated alcohol, we get the alcohol. And importantly, H2O takes a proton, we're going to generate H3O plus. So it's a true catalyst. Okay, so H3O plus is consumed in the reaction, it's also produced in the reaction. So the net effect of this really is alkene plus water gives an alcohol. But without that H3O plus in there, the reaction just doesn't go fast enough to even observe, right? And if you think about this, the reverse of this is the dehydration you guys learned in chapter 7. So the reverse is an alcohol gets protonated, right? We have to protonate an OH to turn it into a leaving group. So your acid protonates the OH, we get water bonded to a carbon, now that water is a leaving group, it pops off, we get a carbocation and water. The water would take this proton, would generate an alkene. Okay, so the acid catalyzed hydration reaction is the reverse of the acid catalyzed dehydration reaction.
Yeah. Wait, going back to what you said earlier, I thought if you didn't have the hydronium ion there, the reaction could not occur, right?
That's right.
Okay, I thought you said for some reason like it would be too fast to occur just now.
No, if you don't have it, right? If you just had water in this reaction, so alkene plus water, nothing's going to happen because you're going to take the alkene to take a proton from water, you're going to generate hydroxide. It's the equivalent of saying if you only have this alcohol, if you don't have acid, right? It still can happen. You could lose H2O and generate an alkene. But hydroxide would have to leave. You'd have to generate a carbocation and hydroxide. And that is not going to be a fast step. It's going to be so slow, in fact, it just never happens. So you got to have the H3O plus in there for this to work. And it's going to be faster the more stable the carbocation is that you generate. And the last thing I'll say, let's see what time it is. All right, yeah, I got a little bit. So, on the reaction with HCl, HBr, I talked about the importance of temperature. Lower temperatures favor addition because the bonds are stronger. Higher temperature favors elimination because it's more disordered and entropy takes a hand. Here, the other thing, let me draw it down here. Both my black pens are starting to go away. You think about this equilibrium, so addition is going to from left to right, elimination from right to left, right? It's an equilibrium. So yes, at lower temperatures, will favor the left reaction. Higher temperatures will favor the going right to left. So that is true. But there's also, let me turn around and face you. There's also, you can invoke Le Chatelier's principle here, all right? We have water on the left. We don't have any water on the right, right? So Le Chatelier's principle tells us, so Le Chatelier is working maybe 40 years after Markovnikov. He was also working on the problem of fixing nitrogen. And what he found is if you perturb an equilibrium, the equilibrium will shift to recover from that, right? So if we have this equilibrium and we flood this with water, we add a whole bunch of water, the reaction will shift toward the right. It'll shift away from the water. Likewise, if we pull water out, the reaction will shift to make water, okay? So we can control this reaction with water, right? So if we have excess water, we're going to favor the right. If we remove water, we favor the left. And you can actually, this is true of any reaction. It doesn't have to be water involved. But in this reaction, if we run the reaction in water, water is a solvent, right? If you think about the way I put this up the first time, H3O plus and water as a solvent, right? That pushes the reaction to the right. If you think about the way I would show this if I wanted to go the other way, And you saw me write this in chapter 7, and maybe, I just concentrated sulfuric acid. There's not much water in there, right? So you protonate the OH, water comes off, then you grab a proton, all right? You don't have a lot of water in here. Right? That's shifting the reaction to the side that produces water. The other way to get rid of water is to boil it off. So if I take this alcohol, put a drop of acid in, and then heat the reaction up in a solvent above 100 degrees, right? A solvent that boils above 100 degrees. Once the water is produced, it evaporates. That's a way to remove water from the system. That's going to pull the reaction to the left. And again, there you have two things. The elimination's favored at higher temperature, and we're pulling water out. If we want to go to the left, if we want to go to the right, we're going to run the reaction with water as a solvent. That is a large excess of water, and we're going to do it at a low temperature. Okay, so Le Chatelier and entropy both give us controls over this reaction. Questions about this at this point? So on Friday, what I'm going to do is talk about some other addition reactions. You should look through chapter 8. All the PowerPoints are up. We'll just start kind of going through them in the order I go through them in the PowerPoints. So today we've done HX, where H is H. X is either a halogen or it's OH. For the OH, you have to use an acid catalyst to make the reaction go. On Friday, we'll see reactions where we use X2, so dihalogen molecules, and X2 in water or alcohols. All right, so that's it from today. Again, I apologize, but it will probably be Monday before I have your exams. I'll post scores, I'll get a key up and I'll post scores as soon as I have them. Don't worry about them. I would say this about everything where results are coming in. Try to live your life and not worry about it until you get an answer. All right? Okay. That's it for today. I will come by